Okay. So good morning, everybody. We will start right now with our last lessons on our workshop on Introduction to HPC. And in the afternoon, we will have the two final, or the last lesson on partial differential equations, this time the relativistic side of that. Let's start here. I will start pointing you to all the links that we will be using. So on demand, I will share with you. Oh, give me a second, I pick up my phone. Okay. So the first thing is open on demand. I will be start sharing my screen. So, okay. So this is the first link right here. This is for entering open on demand. For authority. Just for you to know the equivalent version of that for the other cluster. But we will not be using, well, we will see we can do everything with Thorny. But just in case, when we move to the deep learning stuff, if something happens, if the GPUs are too busy on Thorny, we could eventually want to use Dolly. So this is the link for Dolly. Let me see. Okay, so that's the first part. I will also go into the material, WVU HPC. So here, and if you want to follow that, it is right here. And we will be starting with this one. And the content of this material is on our, okay, let me do something else. The content of the material is in this repository, so I will be copy git. So this, so the command for this, let me see if I can do it. For example, in the Scratch is, let me see, it's git clone this. I will be copying this link for all the notebooks. The content of the material on the web, on the page, on this page, is just a conversion from the Jupyter notebook into Markdown. So it is the same as the notebook. With the notebook, we will interact with it. So that could be better. And so I will be copying the command line that you will execute on Thorny to gather the material for this. So let's start. Let's right here. The first thing that we will do is, let me see if I can do it this way. Going here. I think this one will be better for machine learning. You can select any of those or most of the singularity images here. So what I did was here, here the interactive apps, and I went to Jupyter official images. The reason is because I think for rendering the formulas, there is something that is missing on the module, the Python via modules that was installed on the singularity containers. So I need to check that. And from those here, those are official, comes from Docker containers, and I convert those Docker containers to singularity containers, and I offer the list here, and I update those images from singularity every 3-4 months. So they are relatively recent. And I will use, for example, this one for data science. For sure, we'll have the modules, and the packages, the Python packages that I will be showing today for the concepts in machine learning. And let's say I will select standby, 4 hours, 8 CPU cores, maybe a little bit more. Let's try 10 CPU cores. Most of the things that we will be doing are just single core, with a single core. There are a few things, especially when you start doing linear algebra with big matrices internally, they could be parallelized with all the cores that you ask. So you can get that something. The matrices are big. They could be 1,000 or 10,000, but they are not extremely big. So going into the 40 cores will probably not give you much advantage. Nodes, GPUs, Jupyter Lab, and you click launch here. And remember, for doing that, you clone the repo for the notebooks. I have my own copy here. Well, I will delete this because I have my own copy here. So this is what I will be using here for the machine learning. And we will be covering just the first 2 notebooks. And this is just a portion of an entire workshop on machine learning. So just the first 2. If you want, you can follow the others later. Okay. Okay. So it's right here. Click Jupyter. This is from yesterday. I will go in here to the top of this. It's this one here, machine learning, first section. So you see the content of this is pretty much reflected here on this. It's just a conversion. So here is the same material, but in a static form, just the web page. For the first part, it's not that bad because it's very conceptual. I will go in fast on this because I need to pack 3 notebooks in 3 hours. So it's I need to rush a little bit, or at least going into the main concepts and skip most of the narrative. Let's see. So you can skip all this. So the idea is that why we select that the reason why we select machine learning is because this area is not constrained just for computer science or very narrow area of science. In fact, a lot of new discoveries, new research in many areas of science. It could be physics, chemistry, biology, health science, many new research touches somehow with machine learning, with deep learning techniques, which allow us to learn or to gather knowledge from ways that were previously not possible due to computational constraints, basically. What is the idea of machine learning? Well, view one, let me see if I have that. Not in this now. But this is the metaphor that I present for that. This is something relatively natural to the way we discover things, even historic. So in the old times, say Galileo or Copernicus, they were taking observations, or they use observations about stellar phenomena or about physical phenomena, and start gathering data from them. They already have primitive clocks, but they were putting balls to roll on a slope and measuring the timing for those, measuring this, if the mass has an effect on the timing or the size, or try to reduce some other variables, and they start getting in tables of data. Same thing with the stars. So they capture the positions, so the inclination and the position on the sky of different stars or planets, and try to figure it out what was the real movement of those planets. So what they were doing were gathering data, and from that data they start testing models. So let's say one model could be, okay, assume that the Earth is the center of the universe, which is perfectly okay. You could put the Earth in the center of the universe and start looking into on the movements of the planets, and that's valid. You will get very complicated equations or very complicated movements for certain planets that will go back and forth. They will recall a little bit and they will continue. So that model is okay, but it's super complex, assuming that the planets move, all the planets and the sun, or the stellar bodies move as if the Earth were center of the image. Okay, someone could think, okay, maybe we should try another approach and try to a different model. So let's try to see what happens if we assume is the sun the center of the universe, and what happens with the movement of the planets. So now the equations could be more complex, but the description of the movement of the planets could be simpler, because that moment that will explain that the recul, for example, of Mars is just an effect of that combination of the movement of the Earth compared with the movement of Mars, respect to the center that will be the sun. So they are testing models, and those models are tested on front of data. Well, what we are doing with computers, and after many years, many centuries later, now people start with that knowledge, coding that knowledge into equations, into models that were already prepared on computers. And computers do that. But we learn the model, and we give them the model so it could predict the movement of thousands of asteroids around the solar system and all that. The model was already prepared. It is just that we extend the data for computing those models in a large scale. Now, what we are doing in machine learning is a little bit of the opposite. We are allowing the computer to test models and start adjusting those models, the parameters of those models, based on data. So we give them data instead of giving the equations, the final equation. We are offering data for the model, and the system will start adapting parameters of models for or transformations that could be done to the equations or to the procedures in order to refine those parameters until you get it right, until the computer gets right for the data that was presented. That is the whole idea that we call machine learning. It's not the machine is getting intelligence per se, not yet. It is something that is under discussion, if such thing is possible, or they are just fitting models. I will go into that line. I will not enter into the philosophical questions about if what those newer artificial intelligence machines were doing actual intelligence or not. That is, they could be very, very complex, and they could really trick us to think that something there is happening, that some intelligence is emerging. But we can also consider that those machines are really good at faking the intelligence. So that's another discussion. The main idea here is that machine learning are models that take data and work with that data to refine the model, to fit the model better. So for that, we need some preconditions, if you like, for creating a good machine learning process. So first, having good data. If you have crappy data, let's say you have data with a lot of errors or things, and you don't have a very clear procedure of how to clean the data or how to insert that uncertainty into the model, you will get very crude models for that. So having good data. Having good data is also a good amount of data. So that's another thing. Another thing is having a pattern for the data. It doesn't matter if you try to program a computer to guess what will be the result of flipping a new and the next coin. No matter if you train that with a lot of cases. If you assume that the flipping of the coin is 50-50, well, the computer at the end will guess the result 50% of the time, because there is not a pattern there. On the other side, if something happens regularly, like climate model, let's say, if some conditions are regular and some patterns are present, you can train a model to predict the outcome or predict classify certain set of conditions into a model. So that is another precondition for machine learning, having patterns, the existence of patterns. If the universe were completely random, we cannot do science. The presence of science is possible because there are some patterns behind. And the existence of those patterns, why those patterns exist, that's another thing that most likely lies beyond the domain of science itself. That will be metaphysics or religion. That the existence of patterns. Once those patterns exist, it will be the mission of a scientist to discover those patterns. Those are different domains. So at least the existence of patterns is important. And eventually, the lack of a mathematical model explanation for them. And even when we have the mathematical model for that, sometimes it's good to design machine learning models because they could solve the problem in some cases, they could solve the problem faster than the use of the first principles for solving that problem with the mathematics that we know. So, for example, I have two examples in my mind that are applied in research here at WVU. One is we use machine learning models to predict the structure, the electronic structure of materials, simply because under some circumstances, if you accept some error tolerance, those models can predict the behavior of the material or the properties of the material much faster than using first principles approaches. So that's one case. Another case is people have been using machine learning procedures to predict the behavior of gases without having to compute the whole computational fluid dynamics algorithms and getting patterns that are very, very close to the physical phenomena with a much cheaper computational demand. So all those are cases. So even if you have a good mathematical model, such good a mathematical model, the implementation of the model to the extreme, to the fine detail, could be super expensive, and new machine learning models could get a crude but sometimes acceptable representation of the same thing, so of the same process. So that's another condition. So how we use machine learning process, we use it in several domains, if you like, in several situations. One, for example, classification. Let's say, imagine that you receive electrocardiograms and you want to predict if the pattern of that is consistent with some arrhythmia, some heart condition based on that. So a human expert can see very quickly an electrocardiogram and identify the patterns there. Well, can we train a machine to do that and eventually screen people and classify, okay, this one is the electrocardiogram from someone with an arrhythmia, this one is from someone with this other situation, bulb issue or something. So a classification problem. That's one thing. Or picking images and classify the people if it's this animal or this other animal and try to make such classification. There are apps, for example, on phones that you can take pictures of plants and they will identify or classify the plant that is there, the plant is present. So all that is a classification process. Okay, anomaly detection is when you try to identify cases that are exceptional and they don't follow the pattern. So they are outliers. They fit outside. So we will see that in a minute with some example. Another is dimensionality reduction. Sometimes we have the data. We have a lot of a big table with many columns for example, for patients or for physical phenomena. We have a long list of elements. And we are trying to identify which of those columns are really relevant to predict a certain feature. So we use techniques for identifying which of those columns are more meaningful, or certain transformation or combination of those columns could be better responsible for describing a certain target function or certain target measure that we want. That is another element. Or clustering. Clustering is different from classification. In this case, what we want to identify, for example, is the presence of groupings. Not exactly we know what the grouping means, but it's just the fact that we are able to, from certain, again, for example, many columns, is very difficult for a human for us, that we are constrained to visualize in 2 dimensions, sometimes be able to visualize with computers on projections of 3 dimensions, or sometimes with goggles or things, actually the 3 dimensions, more or less. And with exceptions, some people can visualize things in 4 dimensions. But it is very, 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 very hard to visualize things in 10, 20 dimensions. And ask someone to identify clusters in 20 dimensions, well, that is tricky. You can try to control that with projections, all that, but still there are procedures, computational procedures, that allow the computer to identify that. Beyond that, there are some other things that we can do with machine learning. For example, teach a computer to drive itself. So to drive self-driving cars, for example. So that is a combination of procedures. There is identifying what is in front or around the car, which are the patterns, and identify what could happen and adjust the velocity and the position of the car based on the stripes and the features of the images that the car is capable of gather. All that is also part of machine learning. Well, in general, what we are doing is taking data, taking some general rules or functions, and apply that. So to take the traditional approach is taking some input. We already provide the functions. We already provide the code, and we use traditional programming, so like C, Python, C++, Fortran, all that, to encode the equations, to put those in a computational form, to make a good approximation of those equations under the constraints of computers, which are a limited ability to describe a decimal number, a real number. That's one thing. The constraints on working on discrete space, on discrete time, all that, and try to get a reasonable answer based on that. In the machine learning approach, what we offer is the input data, the output, and inside there is like a very general model with a lot of parameters. So the procedure is there, but it's still with a lot of levers that can be pulled here and there to change how those input data will be mapped to a certain answer. For example, the classification answer or the output, or guiding the car into right or wrong, all that. And we will use this procedure to derive the parameters that will encode somehow the functions, the final functions that will solve the problem, that will produce the right output, the output that is desired for the data that was given. So that is the machine learning approach. Another thing is that we consider machine learning under several subsets. There is like a taxonomy of machine learning. One is called supervised, which is the usual that we present academically, because it's the easiest. Not necessarily the only thing that we do. It's we gather data, we know the results for that data previously, and we offer that to the computer to match the model, the parameters of the model, to the answers that are known. And after, we offer data that was not used for that training to see if the matching is correct. If the matching, that will be the test data. So the test data was not used for building the model, it's just for testing the model. And after we have something that works, and now we can trust that we can present the production data to the model, and it will classify correctly or will provide the solution correctly for the problems, for new problems. Well, the unsupervised learning is a little bit different. You offer the input data, you don't offer answers, and you expect to discover some patterns or some structure, like I mentioned before, the clustering process. So you offer a bunch of columns or a big table with many, many columns, and we ask, okay, can this data, the fields on this data, can be grouped in some clusters based on that, on all those columns, and it will identify in those 2,100 dimensions if there are patterns that could be found that allow us to classify those, to cluster those into groups without training that with known classification. So that is enough. And the reinforced learning, which is often used, for example, for self-driving cars, where we are basically guiding the procedure into, you are doing well, not so well. So you are guiding and you are giving some information to the model about if things are going into the right path or not. But not necessarily a definite answer. This is the correct answer, this is the wrong answer. That is, for example, used in self-driving cars when people try to teach computers to play games, Go, chess, all those things. There are several methods for that, but one case where that is applied is with reinforced learning. Okay, there are here a few words of caution about the importance of error. I will add here also the importance of the ethical conditions of that. I will not go into that, but that is also an important concern on those things, because you can translate with something more, with those models, human biases that could be hidden or explicitly introduced into those models that perpetuate discrimination or the human bias. The human nature could be part of the model, and that's something to pay attention. But we will keep concentrate more on the technical side. So let me see here. I will try to, let me see if I move this. Well, I will rush this, and what I'm doing here is presenting like a very small case here to illustrate the elements of classification. But I will probably skip that. So here what we have is consider, let's say, a set of books with some features there, and I will try to classify that under due to the presence of certain keywords on them. So those are examples of the plots that we use to guide our human understanding on what is happening with the data, which is also part of the interesting thing in machine learning. It's not just give blindly all that mass of data to the computer. It's also a human interaction. We use a lot of visualization like this to identify that something can be done to the data. So we do sampling. Imagine you can have real data, which could be thousands of millions of entries. So we need to gather just a sample of that. So how you sample that is one thing. There are entire books even devoted to the sampling process. And once you do sampling, you try to see if the data offers you some hope of doing something with it. So what we are doing here is from the books, we gather certain words present on those books, and based on them, we try to see if the books could be classified. Just imagine a digital book, and you will like to have like a system that will then identify to which folder should go, biology, chemistry, physics, or something, based on the presence of some words. So some examples of very, very kind of primitive, but still very useful classifier is the key neighbors classifier, which is basically taking the closeness to a certain parameter to the set and use that to classify the group. I am doing it here, but my time is short, so I will rush on that. You can go here and you see here, I'm using one of the libraries that is in Python, and we have it everywhere. We have it on the containers, even for some other things, even for deep learning, we also have there the scalar. It's a popular library for machine learning. It is constrained in the size of the problems that you can deal with. For certain big problems, scikit-learn is not the best choice, and we have other libraries that have been developed for big data. One example is Spark, Apache Spark. Another in Python is called Dash. There are several in Python, and in other languages in R that can deal with much bigger data sets. But for the small cases, for academic purposes, let's say for small examples, scikit-learn is really, really good. So that is what I'm using here. So I am using this library here, scikit-learn. I will not go into the details what I'm doing here, the classifier, to gather, for example, and make the case for one particular book, how it classified the book. And that is what I'm doing here. And describe a little bit the classification. Another thing that I'm doing, for example, is there are several ways of classify those, and here is very, very tiny delta, unfortunately. And but I think if you click on the image and you expand it, I will not do it here. There are different methods for classification, and some of them are better or worse depending on the structure of the data. So you see, for example, when you can really geographically or geometrically separate the elements with straight lines, there are linear methods that are really good for that. So that is, for example, the case here. So an SVN can do such thing. There are some other cases where the values that we are interested in the classification or clustering, whatever, they are like in rings. In that case, linear models will never solve that problem. But there are some other cases, there are some other better models that are capable of adding extra dimensions and eventually separate the points, or simply they are capable of twisting, doing over and over several transformations to the data in such a way that the points naturally separate. That is what is happening here. So here is on the columns are different models here, and how those models represent the classification. So that is what it describes here. So there are other models that are inspired more in statistics, So this is one example, and here are the descriptions of the Bayes theorem and how that was used. And in this case, I'm just presenting the data that we use from pandas. So this is another library that we always attach with this. And there is a very good integration between pandas and sklearn, which are the two libraries, basic libraries in Python for data analysis, pandas, and machine learning, sklearn. In the case of Spark for big data, there is also a link between Spark. Spark is written in a different language. So they have like engines for Python. So you work with Python with the Spark. For R, there is also a couple of libraries, and we have those. We integrate those in our Singularity images for RStudio. We have SparkClear and RSpark for that, and Spark includes a relatively decent engine for machine learning, for classical machine learning is there. And in that case, you can use multiple cores for processing the data, and with the proper arrangement, in really big data, you can use multiple machines from crunching the data on a single program. So that's something that you can do there. Here, the problem of anomaly detection, how you find outliers, so cases that doesn't fit well with the groupings that we can make for them. So all those red dots here under some models could be considered outliers. So they don't fit well under this blob here, or this one, or this one. So identify which one are those outliers. Dimensionality reduction, what I'm doing here is in this very cartoonish way. I have data represented here in 2 dimensions. So I would like to compress the information, or try to compress the information of that using just 1 dimension. So a combination in this case is a linear combination of the two elements here, the X and Y, will give me a line, which is the line here is like a diagonal line, where most of those points line up. And I could eventually describe that instead of the 2 dimensions with just 1 dimension. This is kind of silly on this. It's a very nice for representation. But you can see that if you have 10 dimensions and you can reduce that to 5 dimensions, it's much better to work with 5 dimensions than working with 10 columns of data. So some of them will be the dimensions themselves, or combinations. In this case, it's a combination. It's a linear combination of the X and Y, which is giving me the principal component. That's the name of that, and that is what is presented here. And there's some slopes, for example, the points are clustered together, so you cannot see the difference. But if you go exactly for that line, where the diagonal that is depicted here, you get the better spread of the points. So you can classify them better. You can identify which are the features that are present in those groups. Now, clustering, something like this, and here I am showing with the gift what happens with one cluster model that is often used, the k-means. So what it does is tries to compute the distance to the points. You decide, initially you decide how many points do you want to, how many centers do you want to do, and you start testing the distance to the points to those idealized, or those presented centers. You select the closest one. Based on that, you compute the center of the mass for all those points, and that will be your new center, and you continue that procedure over and over until you get the right centers for all the points. That you see that it is adjusting of more and more the centers of mass, and that is a model that it is very good for demonstration. Look at here that all that you have are the points. You are not giving the centers. You don't know the centers, and you allow the model to start refining the centers, which is the parameters, are the centers of the clusters, with a certain procedure, which is identify the distances and then move the point to the center of mass, and eventually connecting or disconnecting the points to the new clusters. That very simple procedure, but often used. And here, what I'm doing is follow that, pretty much this recipe for something that looks completely unrelated, which are, I think is, let me see. Yes, I think it's not one book, but a set of books, I think. Is this. So they have like the words on a text, and it's trying to identify which are the clusters that we can make from them. So the data is relatively big. It's 50 vectors here, so 50 columns, and I don't remember exactly. Okay, it's our words on a big text. This is the blob vectors that stand for. And I am downloading the material. The material, I think, is also part of the. The file is there, and if you download the materials, the repo is there. It's already there. Otherwise, here is the link where you can search for that, or you can search for a better description of these globe vectors. It's just for making the example of that. So they have many words, and what they are doing is computing distance to words, distance between words. For example, for certain word here, those are the locations, those are the distances, and the system is using the k-means, exactly what we did before here. Instead of 2 dimensions, they are working in 50 dimensions, because what we have here for each word is a vector with 50 dimensions, with 50 numbers. And after the classification, the cluster, they, from that big text and the distance of those, it's able to cluster those in groups, in lists of words that you see they are related somehow. They have some commonality on that. So if you pick one, for example, this one here, you see that all those words are related. Company, stock, shares, Inc., buy, firm, corp, own, all those kind of relate to businesses of some sort, company related words. On the other side, you can see here that Spain, Francisco, Argentina, Jose, Madrid, Santa, those are Spanish words. So that could be now names or proper names of someone, but they are kind of related. With some exceptions here. This gene, for example, is not exactly that, but somehow the method could have false positives here. So in this case, I don't see the relation of those compared to the others. So the system is given a big corpus, a big text, all the distance computed for them. So the vectors, 50 vectors. And you give that to the machine learning model, in this case, k-means, to identify, to group all that somehow. So here you see some of the words, some of the elements that were selected there. And so now let's try to go into a couple of elements, that you can see in more detail. Those are commonly used metrics or functions that are often used in several machine learning models. So one is the mean square error, another one is the mean absolute, how you identify how bad are you between the result that you have and the result that you want. So there are different ways of measuring that distance, and some of those metrics are better or worse depending on the case. So part of the art of machine learning is having a certain intuition on what is the loss function that I should use, which are the ways you introduce transformations in the data, no matter if it's for this case or for deep learning examples. So how you introduce those, you will see in deep learning that selecting a ReLU, people have found that is better than the traditional sigmoid that was originally used for separating, for introducing the non-linearity into the neural networks models. There are newer nonlinear functions that work better for known or unknown reasons. They just work better. But those are functions to identify the losses, and with this, I think I have time, at least half an hour, for showing you the next notebook here, which is in the next section, but I will try to go for another notebook in the time that we have. With one example, let's say, instead of picking randomly different cases, I will use a very simple example, and I will develop different techniques for classification, for clustering, based on the same thing, on the same example. I think it's illustrative of many things. Having the same data and use it for multiple purposes here. So this is the idea. And this is a very commonly demonstrated in academia case of the use of machine learning, and is the iris dataset. The idea behind this is actually interesting. The data was collected by someone here, introduced by this guy, Ronald Fisher here, in a book, based on measurements of flowers in, I think it's Hawaii, Caspi Peninsula, in Hawaii, yes. So we are talking about times without computers. Someone took flowers and started measuring four quantities for the flower. The distance on the petals, on the length and width of the petal, and the length and width of the sepals, so the other sex of the flower. So 4 measurements for each flower, for a total of 50 flowers. And this individual know that those flowers belong to 3 different species of more general kind of flower. And so they have this Iris setosa, the Iris virginica, and Iris versicolor. So they knew which flower is which. And they took those measurements for 50 flowers of each kind. And that became what is called the Anderson iris dataset. So the iris dataset contains 150 rows. If you're thinking like in a table, like in a data frame, we have, in this data frame, we have 150 rows, 5 columns. The first column will be, for example, the species of that flower. The very first 50 are one kind, the next 50 are another kind. And the other 4 columns are the measurements of the sepals and petals of those flowers, the length and width. And the whole problem is try to see if based on that table 150 times 5, we are able to create a model that for any given flower for which we don't know the answer, to which species it belongs, the computer can return the species correctly for the new sample, for the new case. There is another relation with that, because that paper was published on a journal that doesn't exist anymore. That was something that at that time was considered scientific. That was eugenics. And eugenics has a very controversial side of that. Part of that was what at that time people tried to use, for example, human features to try to identify reasons why one kind of people is eventually superior to another kind of people. So why try to justify in a very pseudoscientific way, let's say, if we can identify races based on the size and shape of the nose, of the hair, of the whatever, and attach that to intelligence or certain capabilities, or this or preference, which later was took by the regimes that at that time moved into the Nazi regime, the Second World War, and even today we see the ripples of Nazism and white supremacy still exudated in the wars that we have today in the Middle East, in Ukraine, all those things are still ripples of what was left unsolved 80 years ago. So, and all that is linked to this idea of eugenics, trying to justify one people being superior to other people. So, there are interesting things behind all those. So this is the idea. Those are the flowers, and they have this sepal here and this petal here. So they are measuring this length and the width of this side, this flower, and this length and width of this sepal here. So the two other sides of the flower here. And so here you see the petal here, the sepal here, and they have different measurements. And the whole thing was to classify that. So you see, in the framework of machine learning, what we have are 4 features: the lengths and widths of the sepal and petal, 4 columns. We have 3 classes because we are creating a model that is supervised. So we know the answer, and we will provide that to the model, to train the model, and later to use that model with some of the data that is kept hidden, or eventually when the model is ready for production, we will just ask, okay, give me the 4 measurements of the flower, I will tell you which flower it is. And so that is what we have to offer. So we don't have a specific answer to the computer. Okay, let's say, imagine that we could have that is the petal times 1.5 the length of the sepal, minus 0.3 the length of the petal, and that will give you a number. If the number is between this and this, that will be like a formula for that. We don't know the formula. What we have is the data, and that is the commonality of all machine learning processes. We have the data, and the only thing that we have to offer is big data. 150 doesn't look like much, but that's what we have. And the problem is simple. When 150 we can do things. So here are the citations for all that. If you go to Wikipedia, they will make a longer description and the origins of this data set and the connections to the eugenics and with what we consider like an humanly applied selection to justify society behavior. Okay, representation of data. Here, how you present that. As I mentioned, I have 4 columns. So what I have here, if you think, is a big matrices. And in this case, very simple, because all those columns are measurements in real numbers, so in centimeters, I think to the millimeter. So we have those elements. And if you want, this data set is so commonly used for teaching these sort of things that is inserted into the scikit-learn. So all that you have to do, you don't need to download anything. It's just this line here, and you download the data set. You have the data set inserted into a variable. So now you have here all the keys. So the data set is like a dictionary. You have all the elements here, and you can see here like a statistical description of what is there for all the columns in the set. So the minimal length, the maximal, the mean, the standard deviation, all that. So just to have an idea, which is also good in real cases, because sometimes data could be corrupted or could have wrong data, and you need to clean. So in this case, we are not cleaning data, which is a precondition for that. And that is often the case in those academic examples. We already have all that clean. You had an excellent data set, because there are 50 cases for each one. So we don't have a particular bias on having more data for one case and little data for the other. For example, if we have cases with age where we have people with 130 years or minus 13 years, so we need to clean cases that are really outliers or really wrong data, and we don't know what to do with that. So in some cases, we can suppress negative age or things like that. Okay, so that is what we have here, information about the data set. Here we ask for the names of the features. So this is a data frame. So the names of the columns that we have, okay, those are the names of the columns. What we have as the target names. So we have 3. So, and they put, I think it's a number 013, if I'm not wrong, to the in the 5th column or in the 1st column, depending on the column that identifies the flower, is just one name or one number that decides which kind of flower it is. So this is, for example, one example of the first 5 rows of data. The first 5 rows of data. For the target function, remember the target function is this, Setosa versicolor virginica, and as I told you, the target column is just a set of zeros, ones, and 2. So first thing, if you are doing a sampling of that, which is one of the first things that someone, when receive data, do, it's a really bad idea to just take the first 20 elements for your sample data, because you will get the first 20 from the first species, and you will do nothing. So there are procedures, for example, for doing this randomly, taking a random sample. And in some cases, that random sampling can become really, really elaborated. So just a normal sampling is not random sampling with a normal distribution is not good enough. We need to use different distributions for that. That is not the case here. Just keep in mind that that is something that could be an issue, how you sample this. You don't need to sample this because it's just 150. But if you have 150 million elements, yes, you need to sample somehow. So this is just selecting 2 of those variables and presenting those visually. Something that you do very often in machine learning. So you start exploring the data. You see the data. As a human, you try to see if the pattern is there. And you see, effectively, we have a very good hope here. And so there is a very clear separation for those purple dots. When you just select 2 variables, we have 4 variables, we have 4 dimensions. We are just making a projection. We are eliminating 2 of those columns and keeping just 2 of them, the petal width and petal length. Just with that, we see there is a very, very clear separation. We can somehow make a straight line here somewhere. And we will see later how we can trace a line here. And we say the points on this line below, they belong to this purple flower, although the flower identified with the purple dots. And here we have some mixture here. Some dots are inserted into the yellow blob. And the contrary, there's a couple of yellow dots that are in what we could see roughly as like the cyan blob. So the Setosa is very well identified. The versicolor and the virginica kind of overlap to each other. But eventually, that could be something that is unavoidable, but still we can do a very clean separation, or a relatively clean separation. Maybe the other 2 columns could help us better selecting those properly. So that is another thing. So far, we have not used scikit-learn for anything except for getting the dataset. You have not done any machine learning process at this point. So another thing is that we can present this for all pairs of variables. That's what I'm doing here. So on the diagonal, you will see you have just the same variable. But here we have 2 variables, in this case, the sepal length or the petal width, all those, and try to get the plots on there. So all that is something that we do as a human, not to find a model, but often the case for 2 purposes. One, to raise our awareness of the existence of patterns, so that raise our hope of getting the job done. That's one thing. And eventually to get an idea if there are some outliers, and how important will be to incorporate an outlier detector as part of our procedure in the machine learning process. So those main purposes are in place here. So now we will be using the first machine learning model for classification. It's called logistic regression. The name could be a little bit misleading because the regression is also something important in machine learning, and there are regression models, but logistic regression is actually a classifier. So the idea is that we will be using a function. I think that we have is a function like this. It's a sigmoid. We will be using something like this function, for separate the regions, the two regions of the space, and decide, okay, the elements that lie on the downside of this region belong to a certain class. The points on the upper side, so they go up, they belong to the others, other class. So let me see. This is the mathematical function that we will be using here. So we will be declaring that our X, so our domain will be those elements here. In this case, we will just consider one here. And we will be using the target. We will decide if it's Virginica or not. So do we have two options, 1 or 0? It is or it's not Virginica. Okay, so very simple classifier with just one element, with one variable, and we will try to just decide if it's Virginica or not. So with this, we have points. Those are the points that we have here that we found for that single variable. Some of them are here, some of them are here. And we will try, and we know that all these are Virginica, and all those are from the other two species, so non-Virginica. The whole process here, what we are adjusting here is which is my border for this sigmoid, where I should decide the center of this sigmoid, such that I get most of the elements that are Virginica on the right side of the slope, on this upper side of the slope, and the minimal amount of elements who are not in the downside of the slope, which means having the most of the right positives, the minimal amount of wrong negative and wrong positive elements. So the elements that are misclassified, either because they are Virginica and were classified as non-Virginica, or they were non-Virginica and they were classified as Virginica. Those two cases, we're trying to minimize that. And how we do that? We have just, in this very simple case, we have just one parameter. It's the center of that, of that sigmoid. In this case, when we do this for just one variable, here we are, okay, here we are introducing the element, and here we are using our first machine learning that is inside scikit-learn, which is the logistic regression. We just introduce here the values X, and it will produce a decision boundary. When we ask for the decision boundary of this is just one dimension, so it's just 1 point. The decision boundary is 1.6, 1.66 something. So it's exactly what we got here. It's 1.6. So this element here exactly. In here, we will have 3 points here, 3 elements here that we will misclassify bad here, and 2 elements here that we will misclassify as being Virginica. So We are 2 elements here wrong, 3 elements here wrong. If we move to the right, we will getting less wrong elements in the norm Virginica side, but we will increasing the number of misclassifications in the iris Virginica side, the triangles. We will increasing the number of green triangles that we will misclassify. On the other side, if we move to the left, we will decrease the number of misclassified green, but we will raising the number of misclassifications here on the blue. So what we are trying to do is trying to get the less bad thing that we can do. So it's a little bit like an elections. You don't try to select the best candidate at the end of the day. Most of the time, you're trying to select someone who is the less worse of the candidates that are present. So this is the less worse. So now we have here predictions that we can make just for that case if we offer those 2 elements. If we took a flower and we measured that flower and we got 1.7, 1.5, what we get? So we will be classified that. For this case, 1 will be in the group number 1, which is the green here. And the other, if the value is 1.5, is less than 1.6 for the length, it will be classified as non-Virginic. That is the first classifier using a linear regression. So now what we will be doing is extend that next. It's just now with 2 variables here. And we keep the idea of using just 1 variable for the target function. So this is now what we are doing here. So now in this case, what we have here is a situation like this. We have 2 variables, those, and what we are doing is now to decide the slope and the point for that slope for a line that will be the center of the sigmoid. So you will have, imagine like a surface that is like a sigmoid, like this, but for a surface. It will be down here in this blue area, in this section here, is the flat surface here. Here, closer to this line, it will raise, it will go up. And here on this, it will be another valley, if you like. This is the upper flat place. So we are actually separating the whole space in 2 areas. This area here and this area here, with a function that moves slowly into those 2 regions. Okay. Which now we have 2 parameters, if you want, the slope and the center. Okay. So we will be tuning those in such a way that we try to minimize the number of blue squares that are on the other side and the number of green triangles that are in this other side. So we do that here. In this case, we are using this case. We are using this model, a logistic regression. We offer here, we register here all the values X. In this case, we have 2 columns. Remember, we are selecting just column number 2 and column number 3. So the 2 final columns and the target here. And we will be doing the classification. In a more complex situation, what we can do is to decide here these flat surfaces for classifying the 3 elements. In this case, we are twisting here the space. We have like a flat surface here, flat surface here, flat surface for the 3 different colors. And we have those lines here that are the boundaries of those three. And it's really easy for the yellow. The classification is basically the midpoint between those two. And here it is a little bit more tricky that it's trying to select the best that we can do, but not perfect. And in this case, the model that we use, was here, and the logistic regression. So all those are classifiers. And there are procedures that are based on calculus. So, in this case, I will not enter into much detail on that. There are iteratively adjusting the boundaries, trying to get the best. So that is the whole machinery of that. You know that there is a boundary. It's just you don't know exactly the parameters, and the parameters are adjusted with the solver in this case. There are several, you can see in the documentation, the different solvers that are available, and they basically will perform, they will affect the performance of those models. So, okay. This is more, in this case, to present a little bit what happens in reality, in the real world. When you don't have so much set of data sets, usually what you do, imagine, is that you are piping the data into multiple transformations, cleaners. So at the end, for example, what you do is to clean, removing all those where are missing values. So you take those out. You take some outliers, so you take those out. They could be useful or not, it depends. But sometimes what you do is to take the extreme cases and you move those because they could damage your model. You can serve biases that you don't want. So what you do is to create like pipes where the output, the output of one portion of the model or the function in scikit-learn will be the input for the next section. So this is what I am doing here. I am introducing some predefined transformations to the data before entering into the linear regression. One of them, for example, is this one, scaling the data. So the values sometimes, in this case, probably it's not so necessary, but the values are relatively similar. But in sometimes what you have are values that are very, very dissimilar. So some of them could be on the order of microns or something, and some other values could be in the tens of thousands. And if you don't balance that properly, the models could have really hard time to adjust to different scales. So what you do is, before you present that data to the linear regression classifier, what you do is you change the scale of them. So you ask the model as a precondition to all those different columns to be more or less of the same order of magnitude. Again, something that is here just to present the idea of pipelines in scikit-learn. We are doing this right here before entering the linear regression. And the whole model will be here, the model, which is a combination of transformations on the data. Okay, so, and here we are using all that for the classification. We see if I move, okay, let's move to this. This is programmer sector, and the time is running. And I really want to go into the deep learning thing. So classification. In this case, imagine that we don't know how many species of flowers we have. We just want to know if it's possible to identify the different ones. So we will forget about the target. We don't know that. We will try to classify them, try to make clusters of that. And in this case, I think, which one we will be using? Let's see. Where is that? Okay, right here. So here we are using the key neighbor classifier. So notice that what it does is decides certain regions that it identified. It doesn't, it's not a line, it's just areas based on the closeness to the points that were identified, that they decide, okay, this area here is for Virginica, this area here in the first in cyan or kind of greenish is for versicolor, and this area here is for the setose. This is just a classification purpose made without the logistic regression. Just using the closeness to the values. It will work perfectly, but we will not give you like a functional way of working with this. There is another way of doing this for classification, are very popular, it's very well known, are support vector machines. In this case, what we are trying to do is to find lines, straight lines, that are kind of well aligned to some, imagine rivers. Let me see here. Let me see if they have it in a different one. So what we do basically here is identify, you have points that are close to one area here, to, for example, to this area here, and some other points here. What we are trying to see is which are the points that are closer to the boundary of one of another, and try to find like a narrow or wider path, and try to change the slope of that path such that you maximize the separation between them. And with that, what you get is similar to the logistic regression. You get a line, actually it's a whole band that separates one area from the other. So, and this one was, let me see, here, where we use the model and is a support vector machine. That's what this is doing. You enter the model, the elements X and Y, and I think X continues to be just one dimension. I think yes, one dimension, two dimension, and the value, and we ask, okay, based on those two elements, identify the paths, like the venues, like highways that separate those two sets, correct? Let me see if I have here in one case. Okay, this is just a case with just points. Okay, and this one is the final case that allow me to introduce the first elements of what we will discuss next, which is perceptrons. Perceptrons are one of the original models or mathematical elements that are used for describing neural networks, which is part of a subset of machine learning that is called deep learning. In this case, what we have is like again, could be like a sigmoid that allow me to change the position of the moments. Let me see this way. We would like to have like a linear classifier with a function that will decide if it's 1, it will go to one location, to one class. If it's 0, it will go to another. We have a vector here, and we use that vector here with that function to put the points or the answer to those points into the 1s or 0s. With that, let me see if I can have something practical in example. we will be doing like a linear regression. So we will have in a boundary for all those points, this function will return 1. For all those points, it will return 0. This is a transformation of the data. So the data, instead of them being values that it gets, it will return 2 different values. Well, we can use this better in the next notebook that I will use to put that into multiple layers of those transformations, and those are the building blocks of a neural network. Probably better in the other case. Here, for the dimensionality reduction, we have, again, the 4 columns that we have here, all the data, and we would like to find some combination of those columns that are better responsible for classifying that, for distinguishing those. So we are doing here that all those, you see here what we could. So we will be using something called a PCA, principal component analysis. This is another model that is inserted in scikit-learn in the sense of decomposition. We will be offering the columns. It will do transformation to those columns to get a reduced version of that. So in this case, the reduced version, instead of having 4 dimensions, we will be having 2 dimensions. Those 2 dimensions are not one of the other, the original columns, are combinations of those columns, which are those 2 here. So 0.3 times the sepal minus 0.08, the width sepal. So making that function for the flower, for the 4 columns of the flower, will return just 2 columns, 2 transform columns, and in those cases you get the best separation between the elements with just 2. So you can later attach this model after the principal component to a classifier and get a better result that you do just from taking individual elements, individual columns, like the 2 columns that we use originally. That is another thing that is often used. So you see, this could be linked to the like in a pipe. You remove wrong elements, you adjust, you scale the values, you introduce that into a principal component analysis to reduce dimensionality, and after that you introduce a classifier, and all those are connected. The output of one is the input of the next one. Another case, we use that for k-means. So we use that for clustering. In this case, I'm changing the coloring, unfortunately, but that's the idea. We use that, and we introduce that into a classifier, the k-means. And, well, there is another thing that is shown here, but I probably skip because my time is short. In this case, what I'm doing is some of other possibilities, in this case with digits, with handwritten digits, a very crude representation of those. This is an old data set where what we have are digits condensed in 8 times 8 bits. I think it's 8 times 8 bits. So this predates another data set that is 20 times 28 and is widely used for deep learning. But in this case, it's just classical machine learning. So imagine that, well, from just looking into those, you have an idea that this is a 5, that this is probably 4 or something. That is very crude. It will have a lot of errors, even for a human to make sense of which is the number that is behind. But here, what we are doing is presenting some mathematical foundation for trying to classify that, to trying to identify which of those elements belong to different classes. Here, from a more statistical perspective, but I will be skipping that. That which is important here is this idea of trying to reduce the number of false negatives and the number of false positives that we get. And all that is encoded in different quantities or different metrics that we can take from that. The accuracy is the number of correct samples versus the total number of samples. But there are a few others where they take in account not only that we get something correct, is that we try to minimize those that are incorrect. So the precision, recall, and the F1 that combines those two, the precision and recall, which are different values that we get to identify if the model is good enough. So that is introduced here in this example, but I will probably skip all that for this case. So now what I will be doing now is to jump into the deep learning stuff. Because this is, and we have very short time. I will try to go with this in the 20 minutes that we have, and after I will stop for 5 minutes, and in the last hour or 55 minutes, I will be devoting to another notebook in the deep learning collection. So here, we present what we can see some of the popular models or methods used in machine learning. Machine learning is one subsection of a more general entity called artificial intelligence. So artificial intelligence, a subset of artificial intelligence, are machine learning. You can consider machine learning as different models that do transformation to the data. We call that those transformations in the parlance of machine learning, those are the learning process. When you learn, you transform something, your data, into another collection of information where it's cleaner or it's clearer for you what it means or what it presents. When we are doing multiple transformations to the data, that is what we call deep learning. So that is the origin of the name deep learning. At the end of the day, deep learning is a subset of machine learning, a tiny subset, but still today very important subset of machine learning. That is responsible for multiple transformations, simple, relatively simple transformation, but done massively. And you will see some of the examples that I will present today. Massive transformation. That's why we use computers, not because it's complex, it's because there are too many. Simple linear algebra stuff. It's really simple. Mathematically speaking, what we do is very simple. It's just that we do it many, many times for many, many cases. So that is what the complexity is introduced. Okay. So here I return to what I explained for the machine learning. And those are original tables. So imagine this guy here, Kepler, who took tables, measurements of Mars. This is Mars. So the positions of Mars, different nights, and you try to make sense of all that. So sometimes Mars goes forward, it goes backward. When you look into the sky with a telescope, you find it sometimes compared with these background stars that for practical purpose are fixed. Compared with those background stars, Mars will go forward, sometimes will go backward, down, and after they continues forward. on a slightly different path. So it makes like an S. If you see if you go and see the figures of the path of Mars, it's like an S or a Z. It's something like that. So what the idea here is that we have those tables, and the guy start testing models for them. And those are published. Those are real books where it presents the tables. And what it did was to make a transformation. What happens if my center, my origin of coordinates, instead of being on the Earth, I assume that is on the sun, and the Earth is also moving? How I see things? Well, for doing that, I am making a transformation. When I introduce that transformation, I will see that the figure that I get for the movement of Mars around the sun is an ellipse. So that is a much simpler description from the point of view on the equations that you get at the end. And that moment you say, okay, a better description for the movement of the planets is that all those planets are actually orbiting the sun, not orbiting the Earth. The description of everything orbiting the Earth is okay, but it's more complex. Okay, so, and there are two what I call shores or origins or ways of introducing the basic blocks for introducing what we call deep learning or neural networks. One is the idea of artificial neural networks. This is like a mathematical synthesis of what we think approximately happens on a brain. So again, this is a simplification, a modelization, a mathematical modelization of something that happens on brains, approximately. So this is the idea. You have a neuron. Those neurons could eventually have axons. Those axons could be really, really long. And at the other end of those arms, they have terminals. And the way they transfer information from one neuron to the next one are via carriers, charge carriers, that introduce another charge into the next network, into the next neuron at the end of those action terminals. So those dendrites are connected to some other neurons, and they will go in cascade, moving a current across. Well, what we do is we use that biological knowledge, and we transfer that into a mathematical description of it. What we are doing here is to have an equation where we have multiple elements here, those W that we call weights. They are receiving information, elements, numbers from an input or another neuron, another element like this. And those are here described as numbers that we get, x0, x1, x2. And we multiply those by the weights here. So those inputs that we receive from multiple inputs that we receive here, we multiply those by another number. Those are weights. Those weights are the parameters that we later will change. And at the end, we will introduce what we call an activation function. The activation function is like the sigmoid this function that goes from 0, start climbing, and goes into 1. That is a non-linear function. And the whole trick here in neural networks, in deep learning, is this combination of something that is a linear portion of that, receiving multiple inputs, multiplying by a weight, that is a linear algebra stuff. To this point, it's a linear algebra, pure linear algebra. And only at the end, we introduce the nonlinearity via a function, via an activation function. One of those activation functions is the sigma. Not the only one, not the best one, but usually was the first one that was considered mathematical. At the end, what we get is something that is here in this equation, is the linear, and after this linear algebra stuff, there is also a bias, which is introducing a constant. But again, this is just, if we are working in one dimension, this is the equation of a line, pure and simple. The equation that students in high school learn, equation of a line, pure and simple. Now what we have is the same thing, but in multiple dimensions, but it's still a linear equation. Well, that linear equation used as the input for a nonlinear function constitutes the mathematical model for a neuron, and we call that an artificial neuron. If we link together neurons in cascade, neurons connecting to another neurons, we will be creating what we call an artificial neural network, or to simplify, a neural network. If we know what we are talking about, neural net, right? This is one building block for deep learning, multiple transformations. That's why we call it deep, because each transformation is what in artificial intelligence we call learning process, a transformation, and we are doing multiple transformations. So deep learning, that is the other origin, also mathematical origin of that, is the idea of a perceptron. In the perceptron, what we have is two elements, for example, a classifier, what we introduced before, and we are trying to find a maximum margin, very similar to the maximum margin on a support vector machine. So try to find a line that separates the elements that are in this side of the shore versus the elements that are in the other side of the shore. Which is the best highway that we can build there? Well, there are many ways of doing that. The optimal is that one that maximizes the margin. Well, with this idea, we built a perceptron, and that perceptron is also mathematically equivalent, if we use it from the logistic regression, to what we are doing here. The logistic regression is taking here place of the F. That is historically where deep learning was introduced. But now, what we do in practice are linking all those things that we see here, all these functions here, are here represented as the circles of this neural net. In this case, this is a neural network with one hidden layer. We have an input, and here we have an output. What is in the middle are hidden layers. All those are neurons that they receive multiple inputs. So you see here, this is a fully connected neural network. So each neuron here is receiving the same input values here to produce multiple outputs, the same output that is going into this layer here that is giving the final result. That is what we see. And we can use that for classification, for identifying, for example, in other situations, classifying something that is handwritten, or images, or electrocardiograms, or human responses, all that. In reality, we made this a little bit more complex. We introduced multiple layers. Sometimes some modern neural networks could have even hundreds of layers, and more complex way of describing the connections of those networks. We will see in a minute. I think we will have time to show you some of the convolutional neural networks. And in a few weeks, we will have another workshop. We are planning to offer another workshop that is devoted to, strictly devoted to deep learning. So this is just an introduction. This is just the first two notebooks of this. We will be offering more intense, more mathematically correct, let's say, introduction to neural networks, deep learning, including generative deep learning. So in reality, we have multiple neural networks in layers, multiple layers. And sometimes some of the neural networks that people use for practical purpose, and they are already created. People have designed that, they publish, and after they offer those models could have hundreds, even thousands of hidden layers, and very complex ways of manipulating those, especially in the convolution side. So we will see that, because that is important. So what we are doing here, as a way of describing what we are doing, is, let's try to imagine that we have here are those points in this line here and the points in the red line, and we are trying to separate those. We are trying to identify if a given point here, or separate the areas. So which area should belong to the blue side, the blue area. Imagine that we have points with errors, let's say, and to which point we assign an experimental value. Should we assign it to the blue line, or should I assign it to the red line? Well, a purely linear model will not work. No matter how you trace this with the straight lines, you always would get some of the blue area inside the red region, or the red line inside of the blue region. So we will get a mix. What a neural network is doing is, thanks to this non-linearity, is introducing a twist, is changing the space, is twisting the space. What we are doing here are real examples of the kind of twisting that we do, that those neural networks are doing, in such a way that the whole space is distorted to a point where a simple straight line for that distorted space can help you to identify which areas belongs to which. So that is that. If we return that into the original, you will see that is something like this. It's a curve. It's a curve that in the twisted space, when you twist with the non-linearity, it looks like a straight line. That is the whole thing of neural networks, or the importance of the non-linearity plus the linearity of here. So here, what I'm doing is presenting what happens in a very graphical representation of what the kind of things that you do first with the linear part. What linear algebra is capable of doing? Well, linear algebra is capable of stretching and introducing some skewings, rotations. All that is linear algebra. There are matrices in charge of rotations. The rotation matrix in 3 dimensions is one example. If you multiply the values in the diagonal, so if you have just a diagonal matrix, you can introduce scalings, and more generally, you can introduce skewings. So you change, you not twist, but at least convert the squares into parallelograms, or parallelograms. Well, adding that to the nonlinearity, for example, of the logistic function, is what it allows neural networks to operate, and that is happening at this point. In this figure. At this point, you see that you start at the very beginning. I am just introducing linear functions. I am just rotating skewing, amplifying. And at some point, I introduce the nonlinearity, and you see the straight lines start becoming twisted, start becoming deformed. That is the magic of neural networks. No more than that. Here is another way of presenting what we do. We start with a space like spirals, and the linear algebra side, what it is capable of doing is just doing the skewings, the rotations, and at some point, the nonlinearity is just stretching and twisting the space such that you can clearly separate that with a knife and cutting the space in two. That is the building blocks. Those are the building blocks of neural network. Well, the basic structure is something like this: input layer, one or more hidden layers, and an output layer. And with that, you do classifications, you do all sorts of analysis that are very important and widely used today, again, in all areas of science. I'm seeing this in physics, in chemistry, in forestry, and there are researchers everywhere in WVU who use neural networks for all purposes. So it's not constrained to computer science. In computer science, they are specialized in certain areas that are very with them, like computer vision. That's with them. But people uses those things in other contexts for other kinds of neural networks that we will see. So there is an entire zoo of different neural networks depending on the purpose of them. And so here I gathered this figure that presents a little bit the different kinds of neural networks, and some of them, for example, for trying to compress information or generate the new images, for example. They use something like this. For generative neural networks, they go capture the style and the context, and they separate those things, and they are able to reproduce another image, another figure from a photo with the style of a painter or something like that. I think I have one example here. Other neural networks are better suited for time series, for example, an electrocardiogram, or the temperatures or the weather, making that. Or, for example, those that are used in engineering for modeling the movements of fluids. And all those things that are kind of time related, they use a different kind of neural networks. So here I have examples, the recurrent neural networks, and the feed-forward, which is the traditional network that I show you there, the fully connected. And long short-term memory, also things that are used for time series. And the convolutional neural networks, we will describe those that are specialized for images, for video, for a specific kind of problems where they fit nicely. And okay, and a quick description of the different activation functions. I always describe, and I told you this, and that the usual function that was originally used back in the 70s, because this neural network stuff is from the 60s or 70s. So people introduced that. At that time, the computers were not that powerful for the practical purpose of today. But still, the basic elements came from that age. And they showed they use the logistic function. Over time, people discovered that they could eventually use other functions. Some of them are less nicer from the mathematical point of view, because they are not continuous. They are not infinite derivable functions, which the logistic function is. It has a nice mathematical feature. Some people can survive or be happy with moving away from the infinite derivation and use other functions. Some of them, for example, the ReLU is very popularly used. It's 0 up to a certain point and linear from that point and beyond. And for certain classification purpose, it works much better than this one, than the logistic. Alternatives to the logistic, tangent, inverse, this one that is like a continuous way of the ReLU, the soft plus, all those, and here I'm putting the equation and the derivative of the equation. Some of them, you see, they are not continuous. So, but all of them are widely used, and most of them are now integrated in the main frameworks or deep learning engines that we use today. At a certain point back in the 2000s, we have like 10, 20 different engines. Some of them over time, they have died or they have merged into some other projects. And today, most people use PyTorch, TensorFlow. On the Asian side, they use Paddle. And some others that are like use neural networks on top of those other frameworks, like GDL, MXNet was alive until recently, but there's still some people who use it. So there are a more narrow set of machine learning, deep learning frameworks or engines, and all of them somehow introduce this and many more of those nonlinear functions inside. Okay, that's another thing. Here, what I'm doing, let me see if I can go. Well, I would like to present this. What is happening? Let's see. Can reload this. I don't know what happened. Okay. Okay, what I'm doing here, and you can follow this on your own. I will just describe that, but I will not go into show you the math. What I'm doing here is I am at least once in your life to do this paper-based to get an idea what you are doing, what you are dealing with neural network. So this is a very simple neural network. I have 3 inputs, 1 hidden layer, and 2 outputs. Imagine that I'm classifying something as yes or no, or heads and tails, some classification problem. I am getting something at the end that will give me a number, and I will use to decide what I'm getting. So I am assigning numbers here to the input layer. And what I'm doing here is having some weights and biases for the hidden layer. So this hidden layer, for this neuron, number 1, will have 3 weights here. For the 3 inputs that it receives, it will multiply the corresponding input. For example, this 0.5 with the 1, this one time for the 2, and the -2. And after I will introduce, I was not using biases here. I probably was not using bias, but eventually after that, I could add a certain constant. For simplification purposes, I'm not introducing that. For that result that I'm doing is like vector multiplication, a dot product, if you like, a dot product of this vector here and the vector that I produce here from the inputs. This dot product is what I introduce to the sigmoid, or one of those for this logistic function. If you want to change the sigmoid for the ReLU, it's just a different nonlinear function, and you get a number, 0.13. And you do that for the others, and you are here on the second layer now. Now you do that to the next output layer, who has also some weights associated to each neuron. You do the dot product, you put the result inside as the input for the sigmoid, and you get the final value. If you do that, you get these values here, these values there. Something that you can do at the end is to produce this, to present those values as probabilities, for example, for classification. And at that moment, I think in the next one, I will be doing something like that. So I will skip that. At the end, I want all those values here, for example, that add to 1. And I interpret those as being probabilities of different cases. Probability of being this versus the probability of being that, or 2 options here. And so at least once in your life, you can make sense of what you are doing here with pure linear algebra. And here I'm just using NumPy. So I'm solving this neural network with NumPy. I'm taking the array, reshaping the array, doing a dot product. You see here the dot product here on the input and the weights, no bias in this case. I am at the end for the final layer getting the values here, and I'm getting that here. Okay. Okay, now I introduce biases. Sometimes you can put some values and switch the values to move the values. The reason why we do that is because that allows you to move which is the boundary position, for example, for the logistic function or for the railroad. The bias will move my output from the linear side inside or outside the point where the nonlinearity is expressed or is shown. So that is the role of the biases. Originally I didn't introduce the biases, but now I put it here. And now what makes the whole thing work nicely is that what I would like to do at the end is not just run it once, is to change all that. The whole problem in deep learning is how I change the parameters. They have millions of parameters. In those, imagine with this very, very cartoonish neural network that I have here, I have 3 parameters per neuron. I have 1, 2, 3 neurons, 1, 3 neurons. Each of them, they have 3 weights. And I have just 6. So I have 6 times 3. So I have 18 parameters to tweak, plus the biases, that will be 6. So for this very small, I have 21, yes, if I did it correctly, 21 parameters to change. How I change those? The idea here is to go back, check what I would like to get in the output, and change the weights, or go back and change the weight, such as that if I reintroduce the input again, I will get what I'm expecting to get. So I will be imagining a supervised machine learning problem. I know what I should be getting. So if I introduce the image of a cat, and this one here represents the probability for a cat, and this one the probability for a dog, what I would like to see is that here I get a 1, the probability for a cat. When I present it with the image of a cat, it should be 1. If I am presenting with the image of a dog, I should be getting 1 here and 0 here. Well, what I would like to do is to change the weights of all the neural network for all the pixels of the image, such that the next time that I introduce the same cat, the same image of the cat, I will get 1 here and 0 here. And I hope there is some commonality in the pictures of cats and the commonalities on the pictures of dogs, such that no matter if the picture is different, I should get a probability here that is correct most of the time, as much as possible, closer to 1 for images of cats, closer to 1 for images of dogs here on the other node. So that is backpropagation. Backpropagation is the magic sauce that makes neural networks to work. How I can change all those weights. Well, what I'm using, and I will not go to the mathematical descriptions of that, what I'm basically using is take calculus, applying the chain rule of calculus with partial derivative to start identifying under which direction should I change the weights next time, such that I get a better answer for the neuron that I would like to get in the next step. And doing that backwards. So I start from the finals, I start here. I start on the final side here, changing the weights and eventually bias here, such that the next time I get the right. So identify on which direction of the slope and which direction of the derivative should I use to change the value of the weights up or down, and doing that to the next layer here backwards, and doing that such that the next input get it this right. Here's a quick description of that, of what we are doing. At the end is applying. It's not so simple. It's not that simple as that, but it's applying the chain rule properly with in a way that is computationally feasible. Otherwise, the problem is that is the whole thing. And here is the description of what we would like to do when I say computationally efficient computation of backpropagation. Now, in modern neural networks, what we do is other kinds of networks. And one example of that kind of network is the convolutional network. Convolution is just an operation that we do with matrices. Simple operations. We are always dealing with simple operations. We want the computer to do simple things. We are not asking the computer to do complex things. We are asking the computer to do many, many things, many times same simple things. A convolution is having like a filter, matrix of numbers that we overimpose over a subsection of an image, for example, in this case, an image. Many of those filters I apply at once, and from them we return a smaller section or another, like another image that is a transformation of the original image. Those transformations are usually very complex. Let's say complex in the sense that the image are big. So we apply reductions such that the next time that we apply convolutions, the convolutions are done on a smaller scales, which represents bigger portions of the original figure. So for that, we are applying another common feature here are those poolings that tries to take averages or the maximal or minimal from sections of the matrix to reduce the size of the matrix. So this combination of convolutions, filters on top of portions of the image, and poolings, which are reducing the size of the image to a smaller scale, and connected all those together in cascade is what, and finally adding like a fully connected traditional neural network allows this to do classification. And this is for a very usual example in identifying a digit, convolutions, max poolings, and a final stretching that into a big neural network for classifying that into 10 elements here from 0 to 1, 0 to 9, the output, probabilities. So we will be doing that. So this is an example of a convolution. So, and here I'm doing, and I think I'm doing here, probably not here, not in this notebook. Here I have this filter and I have this picture. So the picture, in this case, black and white. So we have zeros for black and white and ones for white or vice versa. And I have this filter, one filter. Once in the diagonals, once in the contra-diagonal, let's say, and zeros everywhere in the other places. And what I'm doing here is overimposing that image here over here, overimposing that, doing the multiplication element by element, adding that, and I am converting that into a new figure here with a reduced size. So all what happened into this portion is compressed or is collecting in just one pixel or just one square here in my final matrix. I move a little bit to the right, and I am doing exactly the same. I am compacting that. I'm taking element by element multiplication, summing all that. I am storing here the element number 3. That is a convolution. People found that those convolutions are kind of standard, and they capture features of the figure, of the image. For example, in this idea with the dogs and cats, some of those filters give high values by the presence of the pointy ears that are typical from cats, or the kind of eyes that a cat has. All those things are captured and give certain values for one kind of image, while for other kind of images they produce, for example, for dogs, they produce a smaller value. And that helps the classification at the end when you cascade that over and over into narrow images that are covering bigger and bigger byproducts of the filters from the original figure. So some capture edges, the kind of skin of the animal, or all that. But at the end is linear algebra, very simple linear algebra. A computer can do that. The GPUs, which are devices on computers that originally were created for oh yeah, yeah, I need the 5 minutes. So sorry, let's wait for 5 minutes because my throat is tired. And I was, let me see, it is yes, yeah, 5 minutes, and we continue. And thank you for raising my awareness of that. My throat is so I will just wait 5 minutes, and we return and continue with it. Okay. Can we continue? Um, okay. So what I was describing was here the idea of convolutions, which are widely used for images. That is not the only kind of neural networks that we use. For example, in physics, chemistry, people now are using these other kind of neural networks, graph neural networks. I will, in a minute, show you how you access the frameworks. I'm not doing anything really training in this notebook. That's why I don't really need GPUs or anything like that for them. But just to mention that there are some other kind of neural networks, like the graph neural networks, used in certain domains, or the neural networks that are used for creating uh, creating new data, or creating pictures, or those that are used today, for example, for faking the voice, faking the image of someone, the deep fake, or actually making videos with voice, with the, the particularities of a person for all sorts of purposes, from the funny things to the non-so funny things. Okay, and here just this for you. You can read this like a summary of the origins of artificial intelligence back in the 50s or even before, depends on how you consider that. You can trace that artificial intelligence to John McCarthy. I will personally go much earlier to the origins of computing with Alan Turing. Alan Turing for me is the first one who really started describing not the practicalities of this, but at least the conceptual, raising the questions about what it could mean for a computer to have intelligence, for example. What the test of Turing is one of those things that really start posing the questions of a machine having intelligence. Okay, so I will skip all this and I will demonstrate you how you can request GPUs, which are very popular, the practicalities of all that. So if I go, for example, in the case of Dolly Sots, we have here, for those interested in deep learning, you try to avoid doing this with CPUs. CPUs are okay for small neural networks, for those that we use here, for digits or things like that. But for real purposes, for research, model research, you will not use that. You use GPUs. GPUs are cards or chips, usually they are entire cards, that are attached to computers that are originally created for the kind of purposes in games, in visualization, which are linear algebra. That's why they are widely used in neural networks, because they are really good in linear algebra. When you are in a game, and I imagine, okay, Fortnite or some of those games, 3D games, and you are moving around the space, all that you are doing are rotations. And so you are applying a rotation matrix all the time to recompute how the entire world, or you see the world. If you rotate in this direction, greater direction, you move up or you move down. Those are, when you compute the lighting, the shades, all the features of an environment, all that is linear algebra. Attach that to physics engines, which are another chips that are in charge, for example, for designing the flames or the power or gases, expelled gases, and how those propagate, all that. All those, at the end of the day, are very simple mathematical procedures or functions, usually visible in the form of linear algebra. GPUs are really good for that. They have internally, they have like tiny processors. They are very simple, very dummy, but they have many and they are very fast. So for certain kinds of applications, like deep learning, like neural networks, they outperform widely what you can do with a CPU. That's why we use GPUs for this area, or accelerators more in general. So there are some others that are not originally GPUs, but they accelerate. So devices, electronic components that are specialized for linear algebra. We have an entire cluster devoted to that. Is Dolly Sots, this cluster here, Dolly Sots. And here I try to keep outdated the different engines that we have for neural networks. So as you see here, I offer those in an order, let's say. Let me see if you can put it's the longest. Here, for most people will use the area on the top. They will prefer. So a very recent version of PyTorch, TensorFlow. I still support TensorFlow 1.6, 1 point something, because there are people who receive all codes from the advisor that were written years ago with TensorFlow 1, and they want to use it for a while, or they want to compare and translate that into TensorFlow 2, because there are important differences that make those two versions incompatible. So it's not backward compatible TensorFlow 2. And so I am offering those. At some point in the future, in a couple of years maybe, I will be suppressing TensorFlow 1 entirely. So the same as I suppress Python 2 exposed. DGL is another framework. Those are the most popular frameworks for deep learning. PyTorch, TensorFlow. There was Keras, which was very popular here. Now it's integrated with PyTorch. TensorFlow has its own way of doing those things. DGL is a neural network engine or meta engine, if you like, specialized in graph neural network. So that is an paddle. That's another kind of. So I think it works on top of PyTorch. I'm not super sure, but it could work with multiple engines, but they prefer that special kind of neural network. Paddle is an Asian framework. I think the developers of that is from Baidu, which is a popular company, I think, in China. MXNet is no longer under development. I still keep it here because there are some people, or used to have some people, that were working on this. And part of that is geographical, because some of the people who develop or part of the development team for MXNet were I think the Carnegie Mellon or Pitt. Probably Carnegie Mellon, not super, or both. I don't know. And they were part of the team who developed MXNet. But I think that now they abandoned the project, if I'm correct. And those are the images that came from NVIDIA collection. So I took the Docker image optimized by NVIDIA for their own processors. and I add more software to them. So I add some extra utilities, PL, like a image engine. I add more of things to those images, and I pack them and offer those here. If you want just the pristine version, the vanilla version of that, are those here that says no extras. This is just the exact same image collected from the Docker recipe back into a Singularity image and stored here. And we offer older versions here as well. So that is the idea. Most people will be happy with just the first five, probably the first six of those. The very recent versions, they don't care much. They just want to use the latest. And here is the release. So this is the release from June. And they release one per month. At the end of the month, beginning of the next month. So in a few days, they will appear. I will see the 24/7, 07. So, and I update this every 2-3 months. And so not necessarily I will be having the 24/07. I will probably wait until to the 24/08, but I try to keep those updated. So how you use this? In the case of Dolly, and I will see if I can do something like this on Thorny, but I probably have better chances of getting a couple of GPUs or something like that here with Dolly. There are two options: the 2-day and 7-day. This is another machine. This is not everybody have access to this other machine here. This machine has a H100, but most people will prefer to use the 2-day for interactive processing, for testing the models on a smaller scale, and later train the big thing, the real deal, with the 7-day partition. So this is the 2-day partition. I will be asking for, let's say, 2 hours here. I don't have that much time. And I have here, forget about this. This is for another purpose. Most people would like to have an entire GPU. A30s, A40s, A100s. What is the difference between A40s, 30, 40, 100? The best of those, okay, the best of those is for sure the A100s. They have more GPU RAM, and GPU RAM is important, really important, especially for people dealing with convolutional neural networks, with images. Also important for people with dealing in other kinds of networks with time series, like those from an electrocardiogram or time series from experimental data, things like that. When memory is important, sometimes the 24 gigabytes of GPU memory on the A30s and A40s is not enough, and you really need the A100s. Now, the A30 and A40, they have exactly the same memory. They have difference on how they perform depending on the precision, the numerical precision of your neural network, then the weights and biases that you are using. The reality is that in many cases, people really don't need double precision for neural networks. The kind of bias, weights and bias, and the results that they produce are sufficiently good using simple precision. And from those, the A30s, if I'm not wrong, the A30s outperform the A40s. The A40s are slightly better, but only in double precision. So if you are working in single precision, in most of the time in those frameworks, in those PyTorch, you can select that you want to use single precision. Funny thing is, A30s work better than the A40, despite of the name suggests otherwise. But for double precision, the A40s are better. So, and the A100s are better than anything else. on both single and double precision. So let's see, 830 is okay for me. How many GPU cards I will be using? Just one for what the kind of things that I have time in the final 20 minutes. Just one GPU. Sometimes it's good to use multiple GPUs because either you can train different the models under different circumstances. For example, with a bigger batch size, we'll see if we have time for describing what the batch size means. So under different circumstances, you can train different models and see which model works better, or the same model, and they will be working together to adjust the weights and biases. There are different ways of using multiple GPUs, and I'll communicate those to get the results faster. But in this case, I will be just asking for one. Now, the CPUs, the role of CPUs in deep learning is relatively minor in most cases. All the heavy processing is happening on the GPU side. Here, I'm just suggesting a first share. The machines on this cluster, they have 4 GPUs and 24 cores. So ideally, we can think about having 8 CPUs per each GPU that we have on the machine. And I click launch here. And I will be getting, let me see, I don't remember if I have the materials in this cluster. Otherwise, I will try to get that quickly from the chat. Okay. Okay, notebooks, deep learning, and all the notebooks are here. And by the way, I put here in those notebooks, if you want to see, because we don't have time for running on all of them, the framework that is used for each of them. So some of them will use TensorFlow, some other will be using PyTorch. So I have here, and a few of them here. I have one example, and a few examples that use MXNet. So I have a description of which is the right framework for that node. Now, I got here my Jupyter notebook ready, and I will not using this. And I have here deep learning, and let's see if I go with this one. Probably will skip this one. You can see. Let me see if I can do this one or this one. Or I can probably present this one first, not the TensorFlow, and after with discard this. Because this is illustrative and motivate you eventually to look into the notebooks with more care. Here, what I'm doing is applying neural networks that were pre-created, that pre-trained, and sometimes you don't need to train your network from scratch. You just use the work from someone else, and you can just refine the network. So that's what most people actually do. They take like ResNet or AlexNet, those kind of networks, and they just train the final part of the network, the final layers of the network for a classification purpose, and they were just fine. So most of the others are kind of a standard, and they don't need to be retrained. And so you are gaining a ton of time because someone already did the heavy lifting in advance. So here I am not training, but just using a couple of networks to present some of the examples, some of the kind of things that you can do with them. This is the description of this AlexNet. You see a set of poolings, convolutions, Here is a max pooling. Here is another set of convolutions, max pooling, a final dense. This is a very typical neural network for convolutional deep learning. People use. And a stack of convolutions plus max poolings, convolution and max pooling in a sequence of multiple layers of those. And final, for example, for a classification purpose, a final dense layers, a couple of layers with that, and finally a classifier where we assign values with a softmax that they represent probabilities of the different 1,000 options that we are presented from the images. So what we are doing here are all the different, just a list of all the models that PyTorch has internally. I am using PyTorch in this case. So there are a huge amount of neural networks that are already there, that are already presented. So you don't have to invent the wheel from the beginning. You just pick one of those or start reading for what they have been used, what is the strength of that model, how many bias and weights they have. So that will give you an idea how heavy or how hard could be to train the final layers or not, if they serve your purpose for people working on this. In this case, we will be selecting the AlexNet. So that will prepare all this machinery, all this, all that the computer needs to do to create the neural network is right there. They probably tell you, okay, okay. We have the model here. So the model is, you see here, a convolution times the nonlinear side is a ReLU. So convolution ReLU max pooling, convolution ReLU max pooling, convolution ReLU max pooling, a convolution ReLU, no max pooling. Now the images or sub-images are very tiny. So they are just making a few final filters. Now at the end, it goes into a linear network. I don't know, the size of that is 9,000 elements. They go and compress that into 4,000 elements, and they finally compute 1,000 outputs. So they start with images that are 64 times 64, 3 colors, 64, no, 11. I don't remember exactly the size of that. Well, I need to check what is the size of the image that's supposed to get. And at the end, I have 1,000. With that, the original paper that was written, they have to classify like a pool of images into 1,000 classes, and they already have the tags for them. And I think this was for a contest. I don't remember. I need to check that the origin of that. So you have the image. Now, what I'm doing here is taking one image that I found over the internet, and I will see how good it is classifying this turtle, which is a turtle that is native of West Virginia, by the way, the box turtle. And I will try to classify this image with the neural network that was already trained. I'm not changing the neural network. I also taking all the biases here. Okay. Here. So here I am first I build I select the model, and here I am using some biases that are already there, that are already stored in a file. And with them, all the networks, the biases and weights are pre-populated. And that's what I will be using. In this case, let me see. Okay. In this case, I am taking all that, taking a similar neural network, ResNet 101, populating that with the weights, and that is what I will be using for classifying this this image. So I will be first pre-processing the image. So this is what I'm doing. First, I am resizing the image. Most of them are only capable of working with images of a certain size. So I am resizing that to 256, the size. I am introducing some cropping. So I am cutting, concentrated on the center of the figure. I am normalizing the colors. So even if the colors will look distorted for the computer point of view, they work much better if all the ranges for all the colors are pretty much balanced. So that is what I'm doing here. With a certain means of standard deviation, I am changing how those three images, one image is composed by three colors, RGB, I think that they're assuming. So one for the red, one matrix for the red, one matrix for the green, one matrix for the blue. And those are the three images that I'm adjusting the colors. So at the end, what I have are three images, 224 times 224. That looks like this. This is what really is working for the neural network. And this just captured the center. Notice that I cut the right and left side of the image is just concentrated on the center. And just with that is enough. And taking that, I am building that image as a single input, as an array of one element, one image, one case, let's say one case, which is composed with three images, 224, 224, and that's my input for the model evaluation, because the model is already created. So I am using this ResNet. This is the description of the model, how it's built. It's a very big model. I think this model has more than 1 million elements, weights, and biases. It's very big. And I'm getting all those numbers for the what is this actually? Okay, this is the input, I think. And at the end, when I get the output here, I will have 100 elements, 100 numbers. The sum of those 100 numbers is 1, because it's a probability. I think at the end, we see. Yes, they have like the way to convert that into a probability. And here is what I identify in the image. They will have an 87.6% probability, according to the neural network, for this to be in a box turtle, which actually is. And the image is an image that I picked from over internet. Is not the image that was used for training the neural network. But still is capable of capturing the features of the image and assign their very high probability data. In any case, I am here presenting what happens for the next 10, the highest 10 probabilities assigned to this image. So the highest probability is to be a box turtle. The next probability, much lower, one order of magnitude lower, is to be a terrapin, another turtle, the math toroid, which is, it is, but the color doesn't match. Another toroid. So for sure it's a toroid or something related to that. And a salamander, the probability for a salamander is less than 1,000, something like that. And you see the beauty of this. It's just simple algebra, a few nonlinearities, and some of those neural networks already created, and you can use them. I here have another one that was used to change images, which is another cool thing. So here I have, for example, an image and the style, so it was trained with the style of a painter. And I can take an image and recreate how a painter, the original painter, could have painted this landscape with his or her style. So that this is a cool thing. One example that I'm doing here, but I have very little time for going into that, is a different kind of neural networks that takes images. It was trained with images of zebras. And if I present it with an image of a horse, it will put the stripes for that horse and recreate a new image. So here, well, this is the description of the model. It is a ResNet generator, those that are used to generate images, which is one of the things that we will be presenting in the next workshop for deep learning and generative deep learning, how to generate images, sound, video using neural networks. This is the image. This is the image that I will be using. Those are few horses here. So first thing, this thing is capable of changing and identifying which are the horses present on the figure. That is called segmentation. That is part of the things that deep learning is capable of doing. Identify the different elements of a picture. So in the case for a car, for example, where are the signs, if there is a pedestrian, if it's someone with a motorcycle or a bicycle, and what are the locations of those different elements, segmenting the picture that way. So that is one of the things that is capable of doing. But for our purpose, what I would like to do is to take this and convert those horses into zebras. And this is another picture that I'm doing. So in the case when you apply that neural network to this, it will create those stripes here. And here they will try to recreate that with some success. So, and those are images synthetically created from the neural network. Okay. With this, I would like to present you, let me see, tensors, not this one. This one, I will not execute this one, but I will present this one, so it doesn't matter. This one is for TensorFlow, so it will not work if I try to execute it here, and I don't have time to execute the node. If you want, you can execute the node. But for this, in this case, I will have to use a TensorFlow. The idea here is that I'm using different neural networks with growing complexity to try to solve this problem. I have some handwritten digits, and I will like to use a neural network, initially a very simple neural network that they have. Then the images are 24, 24, I think. Yeah, 24, 24, 20, 28, 28, 6,000 images. And I will be using neural networks that will take 64 neural networks into another hidden layer with 64 neural networks to at the end classify that with a softmax 10 options, 10 probabilities that add to 1 to get a classifier. So I have this neural network, a total number of parameters, 55,000 parameters. And here is the description of the softmax with how I need to at the end have probabilities that add to 1. That is what I'm doing here. And here I am presented with an image, and it will return, for example, an image of a 5, and I return a high probability to that to be a 5, otherwise to be a 2. But there is a big difference here. In some other cases, if the image is not so well defined, you will get something like if you take something that is not a number, you will get something like this. So a messy set of parameter values that will not give you a definite answer for that. What I'm doing here is explaining a few things, using this to explain different features of the neural network, the loss function, how you define how far I am from the value that I desire, the value that I would like to see from the training data. So the definition of a loss function, cross entropy loss function. And at some point, I retrained that, and as you see here, the accuracy, how I move, train this multiple times, and I getting higher and higher accuracy with this. And at the end, I am trying to make different, more complex or bigger networks. So what about if I change from 64 to 128? I am making the neural network bigger, not deeper, bigger, just the same tune in hidden layers. And now I have more parameters to tune, 118,000 parameters to tune. And I will be getting a different answer. My losses are better. Now, what happens if I, instead of making the neural network faster, I make it deeper? So I have here 64, I lower back to 64, but I put multiple hidden layers. That's another thing that I'm trying to do. Now I have 63,000 parameters to tune, and I retrain all that. I am getting the accuracy of my training set. This blue line is the accuracy of the training set. This is the set that was used to train them. But I always have under the drawer the test set. It's a portion of values, figures, images that were not used to design or to build, to adjust the parameters of the neural network. Those are used for testing purposes, and you always get a lower value, but this is what you want to get. This is what you want to see for something that was not used for the training. What I'm getting. Otherwise, how much of the results is not learning, but just remembering the output, what should get. The difference here is memorization instead of learning. You know the answer. If I am presented with the same answer and I was told that this is a 5, I return a 5. So same thing here. And okay, the role of overfitting, what I was mentioning here. And I always make the case that with 5 parameters, 2 parameters, I can fit an elephant. And this is actually, mathematically, the elephant is with 4 parameters, I think, 4 parameters, and 4 parameters, those parameters for the elephant, complex numbers, and I fit an elephant. Okay, so the role of overfitting and explain a little bit that. So not thicker, not deeper, what I can do, what else I can do. And here in this table, I am summarizing what I did, 64, 64, 128, or a deeper layer. And here I am taking the whole idea of convolution. Unfortunately, my time is run out, explaining what I'm doing there, the same explanation basically, and now using a convolutional neural network, training with that, and I'm basically getting almost 100% accuracy. You see here at the very end, I think I have a table with different neural networks. And I here at the very, very end, I don't know if it's here somewhere. At some point, I think I missed that. I have a summary where I present the values that you get. Let me see here, no. Dropouts, okay. Another thing that, well, the point is the accuracy is 98% from the very beginning. And you can improve that a little bit with dropouts. We mean cutting some of the neural networks on the fly, so allowing to adjust to avoid overfitting. So this is a nice notebook that presents those. Unfortunately, my time is trying to compact all that information here. You can see on your own. There are some few extra reference for that. And if you want, there is a much bigger description in the other notebooks where I'm going step by step on different elements on other neural networks, the recurrent neural networks used for time series. And now we are preparing a new workshop, an entire workshop devoted to deep learning, where we will be having one session for those graph neural networks and sessions from an entire session devoted for generative neural networks. So this is just an introduction to that, and this is an invitation for that network. So with this, we are finishing the introduction to HPC, the morning sessions. In the afternoon, Irene will present the other side of the partial differential equations for the relativistic case. So another package that is also solving differential equations in a different context, just to illustrate the possibilities of using computers in that domain. So thank you very much. Sorry for crossing the 5 minutes.
Hi, can you hear me?
Yes, sure.
Yeah, I have a this general question. So I would like to thank you conducted this workshop and it was helpful. But besides that, you have also pressed the tutorial. But I was wondering, for example, in the future, if we have any questions or confusion regarding these things, do you have an office where we could come and talk to you or?
Well, you have two things. You can send me an email. Do you have?
Yeah, of course.
Yeah, you have my email, right? It's in.
Yeah.
So you can send me an email. Most people contact me directly in email. You see, we don't have many people in this sort of workshops. So I will not be overwhelmed by thousands of emails. So I am happy to explain questions over email. Okay. We have mostly for the HPC things, we have office hours Fridays. I don't know if you received the message for the office hours. Do you have those messages? Do you know about the office hours? But those are for people who more general questions. They want to know, for example, someone wants to use job arrays and they would like to see. Okay, Daniel just posted the link for the office hours and the ticket system. Some people use the ticket system. Some other people just send me an email and I answer those messages. Those are the usual ways of contacting me for that. So don't hesitate to send me an email asking questions. Sometimes I also call for some classes to give a lecture on a specific topic and biology or something related to HPC. That happens from time to time. But that's it. And there are people who would like to use neural networks for their research, but they are not in computer science, so they don't know much about. So I serve as a bridge. I'm not from computer science either, so I'm a physicist. So So what I do is material science with this machine learning stuff. But I help people who wants to use machine learning or deep learning into their science project, into the research. And so I help bridging that gap and somehow to the best of my abilities. So don't hesitate to contact me even if you
Okay.
want. Are you in computer science or you are in something else?
Yeah, I'm also in physics.
Physics. Okay. Okay. That is okay. So
Okay. Yeah. Thank you. Thank you.
okay, no problem. Okay.